Okay, we're going to continue to answer the question, how do I use tables, diagrams, graphs, and equations to represent quantities that vary together? If you look at workbook page 207, we are going to talk about walking rates. Student 1 walks at a constant rate of 3 feet per second. Student 2 walks at a constant rate of 5 feet per second. The elapsed time and the distance walked for each student vary together. So in this case, we're going to continue to talk about two quantities that vary together, and these two quantities are going to deal with constant speed. We're going to use the variables t and d. T is going to be the number of seconds elapsed since the student started walking, and d is going to be the number of feet that the student has walked. So again, if you remember, we use our variables and we always include units of measure. So t is for time in seconds, d is for distance in feet. If you continue to look at workbook page 207, you can see those two double number lines that show you how the distance and the time are related and how they vary for each student. So with student 1, you can see when when 1 second has passed, because this whole thing here represents 1 second, they've traveled 3 feet. So you can see the little ovals that they've created here show you that from here to here, from 0 to 1 second, in that 1 second time, they walked 3 feet. And so when another second has passed, now you're up to 6 feet. And then as another second passes, now we're up to 9 feet. And then student 2, if you remember, they go 5 feet per second, so their ovals are a little bit bigger because when they go from 0 to 1 second in that elapsed time period, they're going to be traveling 5 feet. Can t and d be whole numbers? So can time and distance be whole numbers? Absolutely. T and d can be whole numbers. So for example, the time could be 1 second, it could be 2 seconds, it could be 10 seconds, it could be 100 seconds. So yes, they can definitely be whole numbers. Same thing for distance. Distance could be 1 feet, 2 feet, 3 feet. So yes, they can definitely be whole numbers. Can they be fractions or decimals? Yes, they can. They can also be fractions and decimals. So for example, time. Could you have maybe even 1.5 seconds or 5 3/4 seconds? Yes, you could have fractions, you could have decimals in there. Could distance be fractions and decimals? Sure. Maybe the distance isn't just 3 feet, maybe it's 3.5 feet or 3.8, 3 8/10. So yes, you can definitely have fractions and decimals. So I'll just throw a couple in, maybe 3/4 seconds, maybe 2.7 feet, that kind of thing. Now, when you have two variables that are related, we can often think of one as the dependent variable and then the other as the independent variable. The distance that each student walks depends on the elapsed time, right? So depending on how much time the student walks, the further they're going to go. That's what makes the distance the dependent variable. Think about the word dependent. It means it depends on something. So distance depends on the time. So distance, is the dependent variable, and that makes t the independent variable. That means it can stand on its own. Keep this in mind, and we're going to talk about this I'm going to highlight this in our takeaways, but when we are talking about the independent variable, the one that kind of stands alone, we're going to use the x-axis when we graph it, and we use the left column of a table or the left column in a table for the independent variable. For the dependent variable, we're going to use the y-axis when we graph it, and it'll be the right column in the table. And you'll see that as we continue to do some more problems. So let's go and write, this is on page 208, let's fill in these tables for those two students, student 1 and student 2. If you remember, student 1 was traveling at a rate of 3 feet per second. So that means when I complete this table, if the independent variable seconds is 0, then the dependent variable, the feet, would be 0, right? Because if no time has passed, then obviously they haven't traveled anywhere. They haven't gone any feet. But if 1 second has passed, now we're up to 3 feet. 2 seconds, okay, now we're up to 6. 3 seconds, now we're up to 9. And you get the idea that each time we're increasing it by 3. Now student 2, on the other hand, they went 5 feet per second. So if 0 seconds has passed, then they've gone 0 feet. If 1 second has passed, well, then that changes the feet to 5. If 2 seconds has passed, then that changes the feet to 10, and so on and so forth. So you can see how the time affects the feet. The time in seconds is the independent variable, it stands alone, and the distance is the dependent variable because it depends on the time. Now we're going to write equations to represent t and d. So I usually am going to set it up so that my dependent variable is the variable that we see first. So if you remember, the dependent variable was distance. So I'm going to say distance equals for both of them. The dependent variable, it depends on the time, right? In this case, we're going to say for student 1, it's time times 3. If you remember from the table, depending on the number of seconds, each time it increased by 3 because student 1 went 3 feet per second. So if it was 5 seconds, we would do 3 times 5. If it was 10 seconds, we would do 3 times 10. If it was 50 seconds that they walked, then we would do 3 times 50, and that would give us our distance. So what do you think student 2's equation would look like? Remember, they didn't go 3 feet per second, they went 5 feet per second. So I might say 5 times t. So if they go 2 seconds, I would do 5 times 2 to get the distance. If they went 4 seconds, I would do 5 times 4 to get the distance. So in this case, in order to get the distance, in order to get the dependent variable, I have to do something to my independent variable. And that independent variable is being multiplied by the unit rate, how many feet they go per second. So how is each student's walking rate related to the equation? Remember, student 1 went 3 feet per second, student 2 went 5 feet per second. Basically, their walking rate is the coefficient of t. Do you notice how the coefficient of student 1 was 3 because they went 3 feet per second? The coefficient for student 2 was 5 because they went 5 feet per second. So the unit rate, their walking rate, is the coefficient of t. It's the number that we're multiplying with the time. Remember how I said that they could be fractions, they could be decimals? This isn't in your workbook, but I want you to try this. Take a look at these two questions. How far would student 1 go in 2 1/4 seconds? Remember, student 1 goes 3 feet per second, so I might plug this into my equation. Distance is equal to 3 times the time. In this case, the time is 2 1/4 seconds, so 3 times 2 1/4. So if I want to figure out how far they'd go, I'd have to do 3 times 2 1/4. That would be 3 over 1 times 9 over 4, because I have to turn my mixed number into an improper fraction. 3 times 9 is 27. 4 times 1 obviously is 4. And I would have to turn that back into a mixed number because I can't leave an improper fraction in my answer. 4 goes into 27, let's see, 6 times, with 3/4 left over. So 6 and 3/4 feet. What if it were student 2? I'm going to do the same thing. I'm going to plug it into my equation. We said that student 2 goes 5 feet per second, and we have to do 5 times the number of seconds. In this case, the number of seconds is 2 1/4. So 5 times 2 1/4, well, that would be 5/1 times 9/4, because I turn mixed numbers into improper fractions. I'm going to multiply across. I'm going to get 45/4, and 4 goes into 45, let's see, 11 times with 1/4 left over. So in 2 1/4 seconds, student 2 would go 11 1/4 feet. Now, this is a combination of 208 and 209. It says on the grids on the next page, graph the data in the tables from exercise 2. Does it make sense to connect the points on the graphs, and if so, connect them? So I'm only going to do student 1 with you. You can do student 2 on your own. If you remember, student 1 went 3 feet per second. Here, at the bottom, you can see the seconds elapsed. Let me just move this guy over here. So the bottom is the seconds elapsed. Remember, we said the seconds was the independent variable. And remember, we said the independent variable is always on the x-axis. The dependent variable is over here on the y-axis. And the dependent variable was the feet, the distance. So, all right, let's graph the points from the table. Remember, we had 0, 0. See if I can plot that. There it is. We also had, okay, 1 second was 3 feet. So right about here. 2 seconds was 6 feet. Right about here. 3 seconds, that was 9 feet. 4 seconds, that was 12 feet. 5 seconds, that's 15. Does it make sense to connect these points? Hopefully you see that yes, it does. It's going to form a straight diagonal line. And it says draw 2 unit rate triangles on each graph. So here's one unit rate triangle. Here's the other unit rate triangle. So how is each student's walking rate related to the graph? This is really important. You're going to need to know this for maybe a quiz in the future. Basically, the walking rate is the length of the vertical side. Remember, vertical is up and down, of the unit rate triangle. So if you look at each unit rate triangle, you can see here's the vertical height. It's 3. Here's the vertical height. It's 3. And if we were to keep going, all of these unit rate triangles are the same. They all increase by 3 because remember, student 1 goes 3 feet per second. That's their walking rate. So the unit rate triangle, the height of the unit rate triangle, shows you the walking rate. So in the equation, the walking rate was represented by the coefficient. In the graph, the walking rate was represented by the unit rate triangle's height. Keep that in mind. You're going to need to know that again. Okay, so what if we changed it up? What if I said it's me? Maybe not a student, it's me, and I'm walking at a constant rate of 10 feet every 3 seconds. What's my unit rate? Remember, unit rate is how much for 1. You know that I go 10 feet in 3 seconds. So I want to know how many feet do I go in 1 second? How many feet per second? I'm going to have to do division. If you remember, to find unit rate, we usually divide. In this case, feet divided by seconds. Feet is 10, seconds is 3. I'm going to have to do 10 divided by 3 to figure out my unit rate. Let's see what happens. 10 divided by 3. 3 goes into 10 3 times. That gives me 9. So that means that my unit rate is 3 1/3 feet per second. So 3 1/3 feet per second. Remember, we said that, our independent and dependent variables, our time and our distance, they can be fractions. They can be decimals. They don't always have to be whole numbers. What equation would I use to represent my speed? Well, remember, the dependent variable usually comes first in my equation. The dependent variable was distance, and the distance is equal to 3 1/3 feet times the number of seconds, time. In all the other equations, we said, okay, student 1, that was 3 feet per second, so we did 3 times t. For student 2, it was 5 feet per second, so we did 5 times t. Well, here, I'm doing 3 1/3 feet per second, so I'm going to have to do 3 1/3 times t. And I can use my equation to figure out how far I would go in 5 seconds, how far I would go in 8 3/4 seconds. I'd have to do, for this one, I'd have to do distance is equal to 3 1/3 times 5, and that would give me my distance. Or if I'm going for 8 3/4 seconds, I'd have to do 3 1/3 times 8 3/4. So I can use my equation to figure out how far I would go in any number of seconds. So here are the takeaways. Remember, the independent variable is the variable whose values influence the values of the other variable. So this is the one that can stand alone, and it causes the other variable to change. It influences the other variable. So if you look at the example that we have here, the cost of gas, C, depends on the number of gallons purchased, G. So the number of gallons purchased is the independent variable. Like if you were to go to the gas station, well, obviously the amount of money that you spend is going to depend on how many gallons of gasoline that you put into the car. So that makes the number of gallons of gasoline the independent variable because it's going to influence the cost. Also, keep this in mind. It's located in the left column of a table. It's also located on the x-axis in a graph. Now the dependent variable, on the other hand, remember it kind of sounds like depends. It's the variable whose value depends on the value of the other variable. So this is the one that depends on the independent variable. So remember that example of the gas? Well, the dependent variable here is the cost of the gas. If we put in whatever number of gallons, then it's going to change the cost of the gas. If we put in 1 gallon, okay, we're not going to spend that much money in gas. If we put in 10 gallons, then we're going to spend a lot more money to purchase that gas. So the cost of gas is going to depend on the number of gallons. And again, very important, the dependent variable is located on the right column of a table, and it's also located on the y-axis. And this is also very, very important down here. Remember, the rate of speed is the coefficient of the independent variable in an equation, and the rate of speed is the vertical height of the unit rate triangle in a graph. So in an equation, we saw the rate of speed as the coefficient. In a graph, we saw the rate of speed as the vertical height of the unit rate triangle.